Tseung's magnetic frame. Tseung has recently produced a subtle design using very similar principles. He takes a magnetic frame of similar style and inserts a permanent magnet in one of the arms of the frame. He then applies sharp DC pulses to a coils wound on one side of the frame and draws off energy from a coil wound on the other side of the frame. He shows three separate operating modes for the devices as follows. Pulse DC in. Pulse DC out. No permanent magnet, no lead out energy, maximum coefficient of performance equals 1. Lawrence comments on three possible arrangements. The first one shown above is the standard commercial transformer arrangement where there is a frame made from insulated iron shims in order to cut down the eddy currents which otherwise would circulate around inside the frame at right angles to the useful magnetic pulsing which links the two coils on the opposite sides of the frame. As is very widely known, this type of arrangement never has an output power greater than the input power. However, that arrangement can be varied in several different ways. Lawrence has chosen to remove a section of the frame and replace it with a permanent magnet as shown in the diagram below. This alters the situation very considerably as the permanent magnet causes a continuous circulation of magnetic flux around the frame before any alternating voltage is applied to the input coil. If the pulsing input power is applied in the wrong direction as shown here, where the input pulses generate magnetic flux which opposes the magnetic flux already flowing in the frame from the permanent magnet, then the output is actually lower than it would have been without the permanent magnet. Pulse DC in. Pulse DC out. Permanent magnet opposes magnetic flux, coefficient of performance is less than 1. However, if the input coil is pulsed so that the current flowing in the coil produces a magnetic field which reinforces the magnetic field of the permanent magnet, then it is possible for the output power to exceed the input power. The coefficient of performance or COP of the device is the amount of output power divided by the amount of input power which the user has to put in to make the device operate. In this instance the COP value can be greater than 1. Pulse DC in. Pulse DC out. Permanent magnet enhances magnetic flux, coefficient of performance greater than 1. As it upsets some purists, perhaps it should be mentioned that while a square wave input signal is applied to the input of each of the above illustrations, the output will not be a square wave although it is shown that way for clarity. Instead, the input and output coils convert the square wave to a low-quality sine wave which only becomes a pure sine wave when the pulse frequency exactly matches the resonant frequency of the output winding. The oscilloscope display shown here is a typical output power waveform which has nearly 390,000 of these pulses per second. There is a limitation to this as the amount of magnetic flux which any particular frame can carry is limited by the material from which it is made. Iron is the most common material for frames of this type and it has a very definite saturation point. If the permanent magnet is so strong that it causes saturation of the frame material before the input pulsing is applied, then there can't be any effect at all from positive DC pulsing as shown. This is just common sense, but it makes it clear that the magnet chosen must not be too strong for the size of the frame, and why that should be. As an example of this, one of the people replicating Lawrence's design found that he did not get any power gain at all, and so he asked Lawrence for advice. Lawrence advised him to omit the magnet and see what happened. He did this and immediately got the standard output, showing that both his input arrangement and his output measuring system both worked perfectly well. It then dawned on him that the stack of 3 magnets which he was using in the frame were just too strong, so he reduced the stack to just 2 magnets and immediately got a performance of COP equal 1.5, 50% more power output than the input power. The transformers of Tseung. Tseung has developed, tested and patented a transformer arrangement where the output power of his prototype is 30 times greater than the input power. He achieves this by using a figure of 8 double toroid transformer core. His Canadian patent CA2594905 is titled Bitoroid Transformer and dated January 18, 2009. The abstract says, the invention provides a means of increasing transformer efficiency above 100%. The transformer consists of a single primary coil and two secondary coils. The two secondary coils are set on a secondary toroidal core which is designed to be maintained at a lower magnetic resistance than the primary toroidal core throughout the entire operating range of the transformer. Thus, when the transformer secondary delivers current to a load, the resulting back EMF is not allowed to flow back to the primary due to the higher magnetic resistance of that flux path. Instead, the secondary coil's back EMF follows the path of least magnetic resistance into the adjacent secondary coil. You will notice that in the following diagram, the secondary transformer frame on the right is much larger than the primary transformer frame on the left. This larger size produces a lower magnetic resistance or reluctance as it is known technically. This seems like a minor point, but in fact it is not, as you will see from the test results. Input power. Primary coil. Primary's coil back EMF magnetic field. Secondary coil 1. Secondary coil's back EMF magnetic field. Secondary coil 2. Secondary coil's back EMF magnetic field. Resistive load 1. Resistive load 2. In a conventional transformer, the power flowing in the primary winding induces power in the secondary winding. When the power in the secondary winding is drawn off to do useful work, a back EMF magnetic flux results and that opposes the original magnetic flux, requiring additional input power to sustain the operation. In this transformer, that opposing magnetic flow is diverted through a larger magnetic frame which has a much lower resistance to magnetic flow and which, as a result, bleeds off the problem flux, sending it through secondary coil 2 in the diagram above. This pretty much isolates the input power from any opposition, resulting in a massive improvement in the operation efficiency. In the patent document, Tseung quotes a prototype test which had a primary coil winding with 2.5 ohms resistance, carrying 0.29 watts of power. The secondary coil 1 had a winding with 2.9 ohms resistance, receiving 0.18 watts of power. The resistive load 1 was 180 ohms, receiving 11.25 watts of power. The secondary coil 2 had a winding with 2.5 ohms resistance, and received 0.06 watts of power. Resistive load 2 was 1 ohm, receiving 0.02 watts of power. Overall, the input power was 0.29 watts and the output power 11.51 watts, which is a coefficient of performance of 39.6, and while the document does not mention it directly, the primary coil should be driven at its resonant frequency. A variation of this arrangement is to attach an outer toroid to the existing bitoroid arrangement, like this. This prototype, as you can see, is fairly simple construction, and yet, given an input power of 106.9 milliwatts, it produces an output power of 403.3 milliwatts, which is 3.77 times greater. This is something which needs to be considered carefully. Conventional science say that there is no such thing as a free meal, and with any transformer, you will get less electrical power out of it than you put into it. Well, this simple-looking construction demonstrates that this is not the case, which shows that some of the dogmatic statements made by present-day scientists are completely wrong. This version of Tseung's transformer is made like this. The way that off-the-shelf transformers work at the moment is like this. When a pulse of input power is delivered to coil 1, called the primary winding, it creates a magnetic wave which passes around the frame or yoke of the transformer, passing through coil 2, called the secondary winding, and back to coil 1 again as shown by the blue arrows. This magnetic pulse generates an electrical output in coil 2, which flows through the electrical load, lighting, heating, charging, video, or whatever, providing it with the power which it needs to operate. This is all well and good, but the catch is that the pulse in coil 2 also generates a magnetic pulse, and unfortunately, it runs in the opposite direction, opposing the operation of coil 1 and causing it to have to boost its input power in order to overcome this backward magnetic flow. Coil 1 input. Coil 2 main output. This is what makes current scientific experts say that the electrical efficiency of a transformer will always be less than 100%. Tseung has overcome that limitation by the simple and elegant technique of diverting that backward pulse of magnetism and channeling it through an additional magnetic path of lower resistance to magnetic flow through it. The path is arranged so that coil 1 has no option but to send its power through the frame as before, but the return pulse takes a much easier path which does not lead back to coil 1 at all. This boosts the performance way past the 100% mark, and 2300% has been achieved quite readily. The additional path is like this. Not shown in this diagram are the reverse pulses from coil 3. These follow the easier outside path, opposing the unwanted back pulse from coil 2. The overall effect is that from coil 1's point of view, the tiresome back pulses from coil 2 have suddenly disappeared, leaving coil 1 to get on with the job of providing power without any hindrance. This simple and elegant modification of the humble transformer converts it into a free energy device which boosts the power used to drive it and outputs much greater power. Congratulations are due to Tseung for this technique.